the next topic we're going to cover is called related rates. And it's actually also another consequence of the chain rule. Now, related rates are usually considered among the harder Calc 1 topics. I thought these were the hardest Calc 1 topic when I took AP Calc. But I have found ways to understand them that I think are better than the ways I first understood them. So I will explain one interpretation as a consequence of chain rule, and hopefully that works for all of you. So now, these examples look like this. Well, first, before talking about the example, this topic is called related rates. So what we're going to do is use the derivative, interpret the derivative as a rate of change. Rate of change, one of our variables is going to be time. So keep that in mind. Our variables are going to be changing as time is changing. Keep that in mind. So let's read this question. A 10-foot ladder is leaning against a wall. It begins to slip so that the bottom of the ladder is moving at a rate of 3 feet per second. How fast is the top of the ladder moving when the bottom is 6 feet from the wall? The first thing I like to do with these questions is draw a picture. I find a picture to be very useful in almost all of these. So first, I'm going to start this answer over here. Once I have the picture, I'll be able to erase this for the most part. First, we're going to draw a picture. 10-foot ladder is leaning against a wall. So here's a wall. We're going to need a ground, so let's put a ground somewhere. And a 10-foot ladder is leaning against a wall. Let's pretend that's a straight line. 10-foot ladder is leaning against a wall. Already, you can see a triangle, a right triangle, has shown up. That will be useful. That's great. A 10-foot ladder is leaning against a wall. The next thing, maybe I'll write 1, draw a picture, because that's usually how I do these. So I'll say 1, draw a picture. 1, draw has a W at the end. Draw a picture. I'm going to get rid of this example. Draw a picture. So we have a 10-foot ladder leaning against a wall. It begins to slip so that the bottom is moving and so on. In the picture, you should label your variables. The variables here are going to be the quantities which change as time changes. So draw a picture. We have a 10-foot ladder leaning against a wall. The ladder begins to slip. The ladder begins to slip. Is this water bottle gonna... No, that's not gonna explain this picture. Maybe this will. A fun noodle. Why do I have a fun noodle in my living room? I might have explained in another video. I use ripped off pieces of this Dollar Tree fun noodle to hold these boards back because the walls are not completely straight and I couldn't get the mounts for the board perfectly against the wall. But what's going to happen here? We have a 10-foot ladder leaning against a wall. Then it begins to slide down the wall. 10-foot ladder leaning against the wall, then it begins to slide down. Some of our quantities are going to change as time is changing. This 10 is always 10, so that does not change. But as this slides down the wall, this distance changes. Which one do I want to label X? I labeled this one X in my notes, so I'll label it X here. So this distance right here is X. As the ladder slides down the wall, that X changes. In particular, it gets smaller. But we'll just note for now that it changes. What else changes? Well, we have a 10-foot ladder sliding down a wall. This other distance on the bottom is also changing. Let's call that another variable. Let's call it Y. So we have two quantities that are changing as time is changing. Well, that's great. In this picture, we will eventually get an equation, but before writing down the equation, maybe I'll write the equation now, why not? Right here we have a picture. We can get an equation from this. It's a right triangle, so you can use Pythagorean Theorem. x squared plus y squared equals 100. So draw the picture, and we'll also get an equation from that picture. Now, one observation to make, I said this before, but now that we have the equation, let's also make the observation. X and y are changing as time is changing. X and y are functions of time. So let's write that down just as an observation here. X and y are functions of time. Since they're functions of time, we can differentiate eventually with respect to time. Let's keep that in mind. The most important thing to observe here is that x and y are both changing as time is changing. Okay, so there's step one, draw the picture. Step two, I'm going to erase part of this board because most of the information is not on this board. Hopefully you've written the question down. Step two, translate the question. It is often said that math and learning math is quite similar to learning a new language. That is definitely the case with related rates. Translate this question into a math question using this information. Now, we're asked to find something. How fast is the top of the ladder moving when the bottom is 6 feet from the wall? How fast is the top of the ladder moving? We're asked, how fast is the top moving? We're asked to find a rate. Which rate? How fast is the top of the ladder moving? Well, x is measuring where the top of the ladder is. X right here, this distance x tells us about the top of the ladder. So we're looking for how fast that's moving, interpreting that using derivatives. What we want to find is how x is changing as time is changing. With derivatives, that is dx dt, the derivative of x with respect to time. X is measuring x is measuring where the top of the ladder is. So how x is changing as time is changing tells us how fast the top of the ladder is moving. Now, the question gives us other information. So we want to find dx dt. When do we want dx dt? Well, what does the rest of the question say? How fast the top of the ladder moving? When the bottom is 6 feet from the wall. When the bottom is 6 feet from the wall. What measures the bottom? Or what measures where the bottom is? Y. Y measures where the bottom is. So this question says when the bottom is 6 feet from the wall. When the bottom is 6 feet from the wall, when y equals 6. What else does this question tell us? It tells us a number 3. What does that 3 have to do with anything? It begins to slip so that the bottom of the ladder is moving at a rate of 3 feet 3 feet per second. The bottom of the ladder is moving at 3 feet per second. That's a rate. Which rate is it? It's telling us how y is changing as time is changing. I'm going to leave a gap here. And I'll say, and the bottom of the ladder is moving at 3 feet per second, so y is changing at a rate of 3 feet per second. So dy dt is 3 feet per second. I'm not going to write units right here. At the end I will. Dy dt, feet per second. The bottom of the ladder is moving at 3 feet per second. Well, that's great. We've translated the question. We're asked how fast is the top of the ladder moving. X measures the top of the ladder. So we're looking for dx dt. at a bunch of certain times. Now, there's one other variable not found in this part 2. Right here in this translation of the question, I like to find all of the variables that I can. If y equals 6, what's x? So we can also find x. When y equals 6, well, x is 8. How do you get x is 8? All of you who said Pythagorean Theorem? I guess that's correct. Although I didn't directly use Pythagorean Theorem. To find that other one, I remembered that a right triangle could have sides in ratio 3, 4, 5 by Pythagorean Theorem. 6 is 2 times 3, 5 is 2 times 5, 6 is 2 times 3, 10 is 2 times 5, so this other one is 2 times 4, which is 8. Or you could have done Pythagorean Theorem, root 100 minus 36, root 64 is positive 8. Because we're dealing with distances, we'll take the positive. Now, once you've set these two things up, you've actually done most of the work. All you have to do now is take the derivative. Now, which derivative are we taking? Well, we're remembering down here, x and y are functions of time. So we're going to differentiate with respect to time. X and y are both functions of time, meaning we have x squared plus y squared equals 100. That's a bunch of t's, let's call it a bunch of t's like that, squared, plus a bunch of other t's squared equaling 100. They're both functions of time. So when we're going to take the derivative, we're going to use the chain rule. So here we have a bunch of t's squared, so the derivative is 2 of them to the first times the derivative with respect to time. X is a function of time. We're differentiating with respect to time, which we'll call t. I guess I introduced t here. That's okay. Plus, y is also a function of time. So we have a bunch of t's squared. So the derivative of a bunch of t's squared is 2 times that bunch of t's to the first times the derivative of the inside, which is the derivative of y with respect to t. And on the right side, the derivative of 100 with respect to t is 0, because 100 does not change as time changes. Well, once we do that, we can go to step 4, substitute, and solve. Now we're going to substitute things from the translation of the question into this equation and solve. Remember, we want dx dt. So we get what? 2 times x, which is 8, times dx dt, plus 2 times y, which is 6, times dy dt, which is 3. So we're just substituting all these numbers here into this equation down here and solving. I'm just going to get rid of the 2 from everything so I don't have to look at that. Divide everything by 2. 6 times 3 is 18. 8 dx dt equals 18. Wow, that's a bad mistake. 8 dx dt equals negative 18. 18 divided by 4. Negative 18 divided by 8 is negative 9/4. And here we'll throw units on it because it's our final answer. In these middle steps, the units would have just gotten in the way. So I'll just not write them till the end. We get negative 9/4 feet per second. So next, we have a spherical balloon is being inflated at 3 cubic feet per second. How fast is the radius of the balloon changing? when the diameter is 14 inches. So we have a spherical balloon. So here, I'll draw a picture, I guess. And sometimes the picture isn't, sometimes I guess it's obvious. This is just a sphere. But we can use the picture to find our equation and the variables which are changing as time is changing. A spherical balloon is being inflated at 3 cubic feet per second. How fast is the radius changing when diameter is 14? Well, we're concerned with, well, maybe I'll get the equation after doing step 2. Because it might not be obvious which function using the sphere is used. So let's translate the question. A spherical balloon is, how fast is the radius changing? How fast is the radius changing? Well, the radius is r, we'll call it r. We're looking for how that's changing as time is changing. So you want dr dt. When the diameter is 14, well, we're looking for how the radius is changing. So we're not necessarily concerned with the diameter. So let's just say when the radius is 7. That's the same as diameter is 13. And what about this other number, 3 cubic feet per second? Well, that's telling us the balloon is being inflated. That's a rate. What does that measure? 3 cubic feet. It's being inflated. That number is telling us how the volume changes. Cubic feet per second. So that's telling us how the volume is changing as time is changing. So dV dt. Now from all of this, we have an equation, or we're going to need an equation with volume. We're going to need an equation with radius. Well, the volume of a sphere is what? 4/3 times pi times the radius cubed. So we want the volume of a sphere. And we want to find how the radius is changing, when the volume is changing at that rate, and when the radius is 7. So we have a balloon that's inflated. The radius is changing, the volume is changing. Well, now we just need to differentiate with respect to time. Remember, the volume and the radius are functions of time. So on the right side, on the left side, the derivative of v is 1. But with respect to time, you need to use the chain rule. So it's 1 times dv dt on the left side. On the right side, well, 4/3 and pi are just constants, so they carry through. But then we have r cubed. So we have 3 derivative of r with respect to time. Radius is changing as time is changing. So we have 3r squared times the derivative of the inside. I just stepped on my fun little. Times the derivative of the inside, which is r, dt. Well, that's great. So now we have to substitute. Before substitute, I'm just going to observe this left side, sorry, the right side. I get left and right confused a lot more than you'd expect me to. The 3's cancel over there. So I'm just going to cancel them now. So on that right side, the 3's cancel, so it's just 4 pi r squared dr dt equals dv dt. But now all we have to do is substitute and solve. So dv dt is 3. 4 and pi are 4 and pi. R is 7. Seven squared is 49. So we have dr dt. I'll write it on the other board. So I'll say dr dt, divide by that number. 4 times 49 is 200 minus 4, 196, equals 3 over 196 pi. What's the radius? Feet? No, inch. Okay. Some of you might have been thinking, why am I not changing units? I'm never going to ask you something where you have to change units. I'm not concerned with your unit conversion skills. Unit conversion is, what, that's a chemistry topic. Well, I guess it's technically a math topic. It's not a calculus topic, that's how I should phrase it. So all of my units will be the same, even if well, whatever. I'm not going to trick you with units. I'd much rather trick you with calculus. So divide by 196 pi, so you get 3 over 196 pi. Radius is in feet. I changed that to feet. And the time is in seconds. So here we had the volume of a sphere is changing. Volume and radius are functions of time. So a dv dt and a dr dt pop up. This is another reason that I like the fractional notation rather than the prime notation for implicit differentiation. Now, this next example is a little bit harder than the first two. Drawing the diagram is a little bit harder. After the diagram is drawn, it might not be. We'll see. At noon, ship A is 100 miles west of ship B. At noon, ship A sails south at 25 miles per hour. Ship B sails north at 35 miles per hour. Find the rate at which the distance between them is changing at 4 p.m. Now, before I draw the picture, it would be worth taking a few minutes to try drawing it yourself with me on pause. So try drawing it and see what you come up with. And then unpause and see how it compares to mine. So first, we'll draw a picture. At noon, ship A is 100 miles west of ship B. So A is over here, B is over here. Ship A goes south at 25 miles per hour. So right here, that quantity is changing. Ship A is going south at 25 miles per hour. Let's call that quantity X. And you could draw an arrow there to show that it's always going. I'm not going to draw an arrow though. Ship B sails north. So over here, it goes north. That quantity is also changed. That 100 is still staying the same, that line. Find the rate at which the distance between them is changing at 4 p.m. I'm going to move this 100 a little. I'm going to move it up here. Find the rate at which the distance between them is changing at 4 p.m. Well, at 4 p.m., ship A is somewhere down here. At 4 p.m., ship B is somewhere up there. So the distance between them is given by that line. That line is changing as time is changing. Ship A is going down, ship B is going up, so that line is getting longer as time is changing. We've already used X and Y, so let's call that other line Z. So right here, we have our drawing. What equation can we get from that? Well, do I want to do that now? Yeah, let's do that now. What equation can we get relating X, Y, and Z? Now, we have these two small triangles. They would be quite useful if we knew something about what happened here between them, but we don't. But what we can do is draw another line. Maybe I'll use a different color. This is blue. Hopefully it shows up. So right here I'm going to draw another line and make another right triangle. I'm going to draw two other lines actually. So right here we now have a right triangle. And let's label it. Well, this bottom is 100 because that's 100 up there. This piece of the blue line here is X. So right now we have an equation relating X and Y and Z because we have three variables now. What is the equation? Well, we're going to use Pythagorean Theorem on this big triangle. So what do we get? We have, what, 100 squared? 100 squared equals that side squared. 100 squared plus that side squared, so plus X plus Y squared equals hypotenuse squared. So we have the bottom is 100. This side is X plus Y. Hypotenuse is Z. So we have 100 plus X plus Y squared equals Z squared. Well, that's great. Let's next translate the question. My black marker is running out of ink. Let's see if I have a new one. Actually, I have about 9 new ones. Next, translate the question. Well, what do we want to find? Find the rate at which the distance between them is changing. What measures the distance between them? Z. So we want here dz dt. When do we want dz dt? We want it at 4 p.m. So we want it at 4 p.m. I already used that last sentence, so I'll just erase it and move this information up. So 2, find dz dt at 4 p.m. Well, what's at 4 p.m.? What are x and y at 4 p.m.? 4 p.m. is 4 hours later. So ship A has been sailing for 4 hours. If ship A sails 25 miles every 1 hour, then in, 2 hours, 50 miles. In 3 hours, 75. In 4 hours, 100 miles. So when x equals 100. So when x equals 100. Okay, there's one of our variables. What about y? What's y? Ship B is sailing for 4 hours at 35 miles per hour. 35 miles per hour for 4 hours, 35 times 4 is 140, 70 times 2. So x is 100, y is 140. We're also going to find z. I'm going to leave that blank for now until we interpret the rates. And then I'll go over and find z over here. So when x is 100, y is 140, z is something else, and dx dt, remember x and y and z are all changing as time is changing, so we're going to need how x is changing and how y is changing. Dx dt, well, this distance and how that is changing, well, that's where ship A is sailing. So dx dt is 25. So dx dt is 25. Similarly, dy dt, y is this distance that's changing at 35 miles per hour. So find dz dt when all of those numbers are satisfied. Now, we need to find z. So let's find z. Z is 260. Where did that come from? 260. Did I just do a lot of math in my head? No. I did some math in my head. Well, actually, no. I knew the answer from over there. But let's find z. So what is z? Let's put a question mark. That looks okay. That's not as good as the one in the previous video. What is z? Well, we have this triangle with z. 100 on the bottom. And what's the other side? Well, the other side is x plus y. Now, you could get it from this equation. I like getting it from the drawing. I don't know, you could get it from the equation. What's this other side? X plus y, 100 plus 140. 240. Now, why does that make z 260? Well, we have another convenient triangle. So there was the 3, 4, 5 triangle. There's also the 5, 12, 13 triangle. This is 5 times 20. This is 12 times 20. So this is 13 times 20, which is 260. Now, you could also remove a 0 from all these if you don't want all those zeros in the way. That's that times 2. That's 12 times 2. That's 13 times 2, and then you throw another 0 on it. So let's use our triangles to our advantage. So now, with this setup, actually I can get rid of all this. Now we can answer our question. All we have to do is take the derivative over here with respect to time. And what do we get? Well, 100 squared is 10,000, I bet. 10,000 does not change as time changes, so you get 0. Plus, what do we have here? X plus y squared. You could multiply that out. I would recommend against that, because the chain rule helps us, well, simplifying it, if you distribute all that out, will take more time, I would guess, than just using the chain rule. So we have a quantity squared, so the derivative is 2 of them to the first power, but then times the derivative of the inside. Remember, we are differentiating with respect to time. X and y and z are functions of time. Derivative of the inside, the derivative of x with respect to time is dx dt. Derivative of y with respect to time, dy dt. Now on the left side, on the right side, we have z squared. Derivative of z squared. Z is also a function of time. Problems like these are why I cross my z's. If I didn't cross my z's, I would confuse myself a lot more than I like confusing myself. But the derivative on the right side, z is a function of time, so you have 2z times the derivative of the inside. And now, we just need to substitute all these numbers and solve. So, I'm going to solve this a little differently than I did before. I'm just going to solve for dz dt immediately and then substitute. So I'll say, so, dz dt, what do I mean by that? Well, I'm going to divide everything by 2z. That's a y that I was just erasing. Divide everything by 2z. Well, that 0 doesn't matter anymore. The 2's go away, and I just put the z on this term. So x plus y over z, leave that alone. And what do we get? X plus y is 240 over z is 260 times dx dt plus dy dt. So what does that equal? That makes 12/13. 50 plus 60, 50 plus 60, what am I talking about? That number plus that number is 60. 6 times 12 is 72. What are our units? Miles and hours. So z is changing at that rate, and I believe that is the right answer. Let's see where did I put my work? Okay, I guess I knew it from over here, not over there. That is correct. So here, our differentiation was more complicated. Our setup was also more complicated. But notice, once we had 1 and 2, we then just differentiated with respect to time and substituted and solved. Now here, the diagram is a little more complicated, and you have to be a little clever in adding those 2 extra lines so that you can get your equation. Now this will be our last related rates example. The volume of a cube is increasing at a rate of 10 cubic inches per minute. How fast is the surface area increasing when the length of an edge is 3 inches? This one is harder, I would say, than all of the first 3. But let's draw a picture. We have a cube. Let's draw a cube. There's a cube. The volume, let's label a side. Let's label it x, because we do calculus with x, so why use the other letter? X is a perfectly nice variable. The volume of a cube. Well, we know we're going to need volume. So let's write down that equation. Now, this also references surface area. So we might also need surface area. Well, we will also need surface area. Let's write that other equation. How fast is the surface area? What's the surface area of a cube? Well, a cube has 6 faces. The 6 faces each have area x squared. So the entire surface area is x squared plus 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 x squared. I think that was 6. 6x squared. Well, that's great. We have 2 equations. Already, it's more complicated than what we did before. Let's now translate this question into calculus. How fast is the surface area increasing? Well, how fast is the surface area increasing? Using capital S for surface area. So find ds dt. Find how surface area is changing as time is changing. So how fast is surface area increasing? When the length of an edge is 3. So x equals 3, and the volume is increasing at 10 cubic inches per minute. So that's telling us how the volume is changing as time is changing. Great. This might not look more complicated than the last one, but I promise you, I think it is. So let's move on to 3. Let's see what happens in 3. Let's move on to 3 at the top of this board, because I think we might need all this space for it. What am I talking about? All this space? We have 3 things here. How could I possibly need all this space? Find ds dt. Well, we have s equals 6x squared. Well, differentiate with respect to time. Surface area, volume, and side length are changing as time is changing. Differentiate with respect to time. Derivative of x squared, 2x, so we get 12x on that side, times the derivative of the inside, dx dt. So ds dt equals 12x dx dt. So now let's substitute. X equals 3. Dx dt equals not 10. 10 is dv dt. We don't know dx dt. But we have information that will allow us to figure out dx dt. So I'll put a question mark there, and above average question mark there. If you didn't watch lecture video 8.1, you have no idea why I said above average there. If you did, odds are you do know why I said above average there. So we want to find dx dt. Well, to find dx dt, we're going to use the volume. And we're going to differentiate that with respect to time. So I'll say diff with respect to time. What do we get? Well, we get dv dt equals 3x squared dx dt. Well, that's nice. There's another dx dt. Maybe we'll be able to solve for that by substituting. And yes, we will. dv dt is 10 equals 3 times 3 squared times dx dt. So substitute dv dt is 10. We have that here. Substitute x equals 3. We have that here. So we get 10 equals 27 dx dt. Divide by 27. So you get dx dt is 10/27 units of some kind. I don't know, feet and inches or feet and minute maybe. I don't know. But we have dx dt is 10/27. Well, now we can substitute that over here. So 12 times 3 times 10/27. So that equals, what does that equal? That 3 is going to cancel with that 3. That 3 is going to cancel with that 3. We're left with 1 3 in the bottom. We're left with a 10 and a 4 on top. So we get 40. It's a 0. So we get 40 thirds, whatever our units are. Let's get the units right. We have inches and minutes. And this is surface area. The units on surface area are squared because surface area is squared. So we have inches squared per minute. Now for this one, we had to do some side work to find one of the rates. In the other 3 examples, we had to do some side work to figure out one of the variables. Here, we had to use the information to find one of the rates. So try, I think there are 3 of these on the worksheet. Try these. I don't think these are easy questions. They definitely take some getting used to, so see how they go.